Hey everybody, welcome back. This lecture is all about, well, addition. We're just going to be talking about adding up stuff. Well, of course, a little bit more than that because this is calculus, right? There's going to be limits involved because what we're going to do is we're going to add up stuff, but we're going to start to add up things that are getting really small. Like before, we would take a limit and we would have small distances between things. Remember, close only counts in horseshoes and hand grenades and limits, right? So we we're going to be adding up things, and we're going to be adding up numbers that are getting really small. So first, a bit of notation. So you may have seen this sort of thing before with a big capital letter sigma to mean the sum of things. Right? So here's what we're gonna have. We'll have a big sigma, right? And then something written below it, like I equals 1, and something written above it, like n, and then out to the right of it, the things that we're going to be adding up. And what that means is we run the I from 1 up to n. In other words, we start out and we say I is equal to 1. Okay? When I is equal to 1, then we look to the right and see what we have to the right. And whatever we have there, we plug I into that. If we have, in this case, like a list of numbers like A1, A2, A3, A4, then what we would do is we'd grab the first number, the A1. We'd write that down, and then a plus sign, and then you'll get the second number. So we'd let I equal to 2. Plug I equal to 2 into that and see what we get. Get the second number. Then a plus sign, then let I equal to 3, and so on. And we keep going until I gets all the way up to n, whatever n is. And then we get that number, and that's where we stop. We add up all those numbers we've collected. That's our sum. Okay? So to give all these different pieces names, and again, this desperately needs an example, and so we'll definitely get one of those in just a second. But before we go on to an example, just so that we're all clear about the names of all these pieces, we call that I the index of the summation. In other words, it's just the number that's changing as we go through, picking out all the terms we're going to add up. And that a sub I in this formula, that's the ith term. So in other words, you'd have a first term, a second term, a third term, and so on. A1 would be your first term, A2 would be your second term, and so on. The I equals 1, right, to n, tells us that our upper and lower bounds of the sum would be, well, n is your upper bound and 1 is your lower bound. You start from I equal to 1, and you go until you get to up to I equals n. Okay, so I said this desperately needs an example. So here's a really easy one. So we have the sum from I equals 1 to 6 of just I by itself. So just plain I. Okay. So that means we need to start out, we let I equal 1. I plug it into the expression there to the right of that big capital letter sigma, and that expression is just I. So that's easy enough. So I get, when I plug 1 into I get 1. So that's my first number, is 1. Then I'll let I equal to 2. That'll be my second number because I'm just adding up the i's. So then the third number, well, I will be 3, so the third number is 3, and so on. And I keep going up till I get all the way up to number 6. That's my last number. And I add all those numbers up. Here's a really, really nasty looking one. But doing something that's this gross may be a good thing for an example to let us see, exactly where all the pieces go. So in this one, we've got several different variables, right? So our index here is not I anymore. We've switched to using K. We also have these n's floating around, but again, they're just other numbers. So what we're adding up is 1 over n times k squared plus 1. Those are the things we're adding up. And we're letting the k change. So first off, k is equal to 1. So I plug 1 into that, and I get 1 over n. And again, it's supposed to be k squared plus 1, but we start out with k equal to 1. So I'll get 1 over n, 1 squared plus 1. Whatever that is, that's my first thing I'm adding. So write that down and a plus sign. Then I let k equal to 2. I plug that in there for k, and I get 1 over n, 2 squared plus 1. Then I let k equal to 3, and I get 1 over n, 3 squared plus 1. Then k will be 4, so I get 1 over n, 4 squared plus 1. It's getting kind of boring, right? I keep adding all those things up until k reaches n. And so when k is n, I get 1 over n, and now the k's become an n, so n squared plus 1. Now you may go, that's really weird because n's still a variable, and it is, right? I don't know what n is. What do I do? Well, you just leave n in there as a variable. That still works. And we'll see examples later where we're going to have things that ugly and we're going to want to be able to work with them. But when we do things that are that ugly, the kind of sum we're going to have is going to look more like example C. So in this example, the thing that I'm adding up is f of xi. So in other words, we have a whole bunch of different x's, x1, x2, x3, x4, and so on. And I'm plugging those different x's into my function and multiplying by delta x, whatever that means, right? Well, we've seen delta x's before when we were doing, delta x over delta, or delta y over delta x. We were finding slope and things. That's obviously very closely related to what's going on here. So all we have to know at this point is that big sigma is telling us to add up the thing that comes after it, which would be, the ith x, so x of I, times delta x. So my index of summation says we start with I, and I is the variable, I equal to 1. Okay, so I plug 1 into that. That gives me f of x1 times delta x. And again, imagine these were a whole bunch of different x's and I've got them numbered. That's the first x. Right? Then we go to I equals 2. I'll get f of the second x times delta x. Then I will be 3. I'll get f of the third x times delta x. Then I will be 4. I'll get f of x4 times delta x. Keep adding all those up, all the way up until I get to n, right? So I'll get f of xn delta x. Okay? And again, I don't know what that's going to add up to be. It depends on what my function is. Right? But that kind of a thing will turn out to be really important in just a few minutes. Okay, it's probably useful to go ahead and give you some cool formulas that will be handy when you do the homework. So here's an easy one. Suppose C is just a number. Like, imagine C is just 5. And I add up 5 n times. So in other words, I will go from 1 to n. Right? And so as I go through and I add up things from 1 to n, I'll just have 5 plus 5 plus 5 plus 5 plus 5. Now think about that. If I go 5 plus 5 plus 5 plus 5 plus 5 plus 5 n times, well, that's sort of the definition of multiplication, right? If I add up 5 n times, that's just 5 times n. Okay? So same thing here. If C is my constant and I add it to itself n times, right? C plus C plus C plus C plus C. Then after I've added up n of those, I get C times n. That's exactly what multiplication means. What if I do what I was doing in that last example, where I just add up I? So in other words, what would this look like? Let's say that n were 100. Okay, then this would mean I'm adding up just the numbers 1, 2, 3, 4, 5, 6, 7, all the way up to 100. That's a horrific, horrible, awful thing to have to add up. But we have a shortcut. It turns out that that's just 100 times 101 over 2. In other words, or in general, if we want to add up all the numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? That's I, and I goes from 1 up to n. If you add up the first n numbers, you get n times n plus 1 over 2. Now, where does that come from? It's really awful to try to do this with the way that you would see this in an upper division class in introduction to proof, where we teach people induction, and that takes us far away from what we want to do. But I'll give you a very quick story and I think an explanation which will make this make sense. So apparently, when Friedrich Gauss was one of the very most famous mathematicians of all time, lived in the 1700s, was, in fact, some people say he was sort of the last mathematician that knew all of math, because after his time, there's so much math that no one person could know it all. But people, say that he probably did know everything that there was to know, when he was still alive. When he was a child, he was misbehaving in school one day, and his teacher said, Carl Friedrich Gauss, get up here. And she said, here's what I want you to do. I want you to sit down and I want you to add up all the numbers from 1 to 100. And thinking this will take forever and will, be awful and boring and a suitable punishment for a kid that's being loud in class. And he stops for a second and he thinks, and he tells her the answer. And of course, she was flabbergasted. But what he did was exactly this trick. And it's not clear exactly, how we figured it out because there's lots of different ways to come up with this formula. But here's probably the easiest one. If you think about it, think about the numbers from 1 to 100. If I were to pair them off, right, and do this in a clever way, this becomes really easy. For example, let's grab 1 and 100. Now stick those together, and obviously I get 101. But then we go in a notch. In other words, I grab 2 and 99. Okay? So, oh, wait a minute. 2 and 99 is also 101. So then go and grab 3 and 98. 3 and 98. Ooh, that's 101 also. See what's happening? Right? Then we go grab 4 and 97. That's 101. 5 and 96. That's 101. See? And so what I'm doing is I'm pairing up all the numbers. So I'll end up with 101, right, for each pair. How many pairs are there? Well, I've got 100 numbers, and so there's 50 of them. In other words, if I look at the formula, that's where the n over 2 comes from, because that's half of the numbers I'm adding up. And doing that little pairing trick, I get n plus 1. So n plus 1 is what each pair adds up to, and of course, because I'm doing this in pairs, there's only half the numbers to add. So it's n divided by 2. That's where that comes from. Okay, so the next formula I want to give you is what happens if you add up all the squares. So it would be like adding 1 squared plus 2 squared plus 3 squared plus 4 squared and so on. Yuck, that really is awful. There is an easier way to do that than just sitting down with arithmetic and suffering. And here's our formula. You would just do n times n plus 1 times 2n plus 1, all divided by 6. That's much harder to explain where that comes from, and I'm not going to attempt to do that now. But if you're really curious, you can look that up online. If you take other classes in number theory or discrete math, or even sometimes in Introduction to Proof, you'll see where this formula comes from. We could try this again with cubes. So 1 cubed, 2 cubed, 3 cubed, 4 cubed. And there's a fairly simple formula for how that works. Adding all those up from 1 to n, you get n squared times n plus 1 squared, all divided by 4. So keep those formulas in mind. You'll need those in the homework because there'll be places where we want to use those to simplify a nasty, ugly sum.